In 2006, the engineering focus in Detroit, Stuttgart, and Toyota City was entirely physical. Automakers were trying to figure out how to mate an electric motor to a gas engine, or how to get an early smartphone to integrate with a dashboard. Meanwhile, in corporate finance departments, executives were watching early economic indicators flash red. The pressures that would eventually trigger the 2008 financial crisis were already squeezing margins. When capital gets tight, timelines shrink. The strategic planning window across the industry contracted to a strict 3 to 5 year cycle. If a project couldn't deliver returns within half a decade, it was cut. This combination of heavy mechanical engineering and immediate financial stress consumed the entire oxygen supply of the global auto industry. Nobody was looking at abstract computer science research. But even if they had been looking, they wouldn't have seen much. In 2006, inside the computer science departments of major universities, bringing up neural networks was a quick way to stall your career. The mainstream artificial intelligence community had moved on. The focus had shifted to support vector machines and Bayesian methods, approaches that offered rigorous mathematical proofs and immediate, reliable results. The academic environment was actively hostile to neural network research. Funding agencies denied grant applications. Major conferences routinely rejected papers on the topic. Professors explicitly advised their graduate students to pick different thesis subjects if they wanted to find jobs. The specific algorithmic architecture that will eventually power autonomous vehicles and factory robotics was sitting in the academic discard pile, written off by the smartest people in the field as a dead end. 3 researchers refused to accept that consensus. Geoffrey Hinton, Yann LeCun, and Yoshua Bengio formed a loose, isolated network of collaboration, stubbornly keeping the intellectual tradition alive. Working with a small group of devoted students at the University of Toronto, Geoffrey Hinton continued refining neural network architectures. In the United States, Yann LeCun was proving these systems could actually work at scale. He deployed convolutional networks to read handwritten numbers, automatically processing millions of bank checks throughout the 1990s. Back up in Montreal, Yoshua Bengio was advancing the underlying math, focusing specifically on how to train complex, multi-layered architectures using probabilistic generative models. This work required money, and the standard American and European agencies had shut off the tap. The lifeline came from the Canadian government. A modest grant program called CFAR provided just enough institutional support to keep their research moving. This small ecosystem of researchers and institutions preserved the talent and knowledge that would eventually transform the global automotive landscape, surviving on modest funding while the rest of the world moved on. The thaw began in 2006. Hinton and his student, Ruslan Salakudinov, published a paper in the journal Science. They demonstrated a reliable way to train networks that had many sequential layers of artificial neurons. This diagram illustrates their solution, a technique called greedy layer-wise pre-training. Instead of trying to train the entire network at once, they trained it one layer at a time. The first layer learned basic edges, the next learned shapes, and so on, building a rich hierarchical understanding of the data. By stacking and stabilizing these layers, they bypassed the computational bottlenecks that had plagued researchers for years. The network could finally utilize its own depth to process information without the math collapsing. Because the phrase neural networks still carried heavy academic baggage, the researchers started using a new term to describe these multi-layered architectures. They called it deep learning. This 2006 paper remained a piece of theoretical mathematics, far from becoming a commercial product, but it proved that depth mattered, cracking a door that had been shut for 20 years. Meanwhile, nobody at Ford, Volkswagen, or Honda was reading the journal Science for algorithms. The global auto industry was completely unaware that this paper existed, yet the lineage is direct. Every camera-based driver assistance system on the road today and every computer vision tool inspecting parts on an assembly line relies on the multi-layered architecture proven in that specific publication. If those 3 researchers had listened to their peers and abandoned neural networks in the 1990s, the underlying math wouldn't have been ready when the computing hardware finally caught up. The development of autonomous driving would have been pushed back by at least a generation. This sequence reveals a pattern. The most consequential automotive shifts often incubate in isolation, far outside the recognizable corporate supply chain, remaining invisible until they emerge as finished technology. The computer science community eventually recognized this persistence. In 2018, Hinton, LeCun, and Bengio were jointly awarded the Turing Award, computing's highest honor, and became widely known as the Godfathers of AI. But back in 2006, the victory was quiet. The mathematical barrier was broken, but the technology remained confined to a handful of university labs. In a Toronto lab, Geoffrey Hinton was working with a graduate student named Alex Krzyzewski, who was studying how to apply these new, deeper architectures to images. 6 years later, Krzyzewski would write a piece of code that forced the entire global automotive industry to pay attention. The intellectual fuse lit in 2006 was burning down, preparing to trigger a technological explosion that Detroit and Stuttgart could never have predicted.